Hello everybody, this is Doug, and in this very short video I'm going to talk about a slight issue that you can run across with allylic hydrogenations. So let's talk about allylic hydrogenations. First of all, I just want to remind everybody what we mean by allylic, right? Allylic is a position and it's one away from an alkene, right? So if you find any alkene, you got to have an alkene in a molecule. One away from it is allylic. These positions are allylic. Right? On the alkene are the vinylic or the vinyl, and then one away from a benzene ring is benzylic, right? Those are the different sort of names for being close to alkenes, CC double bonds. Now, allylic positions are nice in brominations because they're very stable, right? Because you form a resonance stabilized carbocation. So you might, or not carbocation, radical. So you might imagine at some point there's going to be this intermediate here where you form a radical here. Right? Because not only is it secondary, which is better than being primary, but it's also allylic, so I'm able to draw resonance structures, right? I can have, let me kind of make this look like they're a little more attached. You can have this electron combine with this electron, and this one move over here, drawing your resonance structure. I'm trying not to get frustrated with my program. It just does that. That's okay. We're good. Where you have like resonance structures, right? And then at some point, a bromine is going to go onto that position. So you'd expect to get quite a bit of this product where you've brominated the allylic position, right? Now, the problem with allylic brominations when you do this and you just add Br2 is that you're also going to get a whole bunch of this product. Right, where you end up adding Br2, where you end up brominating that alkene and not doing really a radical bromination. And if you remember, right, that just comes from that reaction you learned before where we said, okay, well, if you have an alkene and you add Br2 or Cl2 or whatever, you end up adding two bromines, right? They're antimarkovnikov and they have an anti-addition. So I'll draw the enantiomer for this one. So you're going to get, right, the addition. You're going to get the addition of Br2 to the alkene. And so that's a problem with just adding Br2 to do these allylic brominations. The solution is that we use NBS instead. And NBS is this molecule. It's N-bromosuccinimide. Let me draw this out a little bit better for you. It's N-bromosuccinimide. So succinimide is basically this, but with an H here, but N-bromo means that there's a bromine on that nitrogen. And what's nice about using NBS, right, so this is NBS, N-bromo succinimide. What's nice about this is this basically produces bromine radicals. Right, it produces bromine radicals without adding Br2. So I don't need to make my bromine radicals from Br2. I can use a molar equivalent, or a little more, of NBS to do these brominations. And so what you end up getting with this is that you get that allylic bromination like you want. And then I'll put just parenthetically here, very little or no bromination product. Right, so you're not going to see a whole bunch of this where you added the equivalent of two bromines. You're not going to see it. Basically, it goes through a different sort of mechanism. I can show you in class if you want, or you can just look it up and just Google it, or it's in the book. But NBS is a way to get bromine radical that doesn't involve Br2. And if you don't have Br2, you can't do the bromination of an alkene. So it's kind of a nice reagent. You're almost certainly going to see it. It's written out NBS. You can write NBS, or you might see the whole molecule drawn out like I have down here in the bottom left. That's what the molecule is. Now let's take just a look at a few examples using NBS. Right, if I take this cyclohexene and I add Br2 and some peroxides, in this case benzoyl peroxide as my initiator, again, the idea is that I'm going to get some of that, I'm going to get the product that I want. I'm going to get some of this allylic bromination, right? Because again, remember that these positions right here, these are the allylic positions. That's the most stable place you could form a radical. And bromine is very selective when it comes to where you're going to form that radical and where the bromine is going to end up. But the problem is that you're also going to, right, because we have Br2 in this case, because it's Br2, we're also going to have some product where you just straight up added the Br2 across the alkene. So maybe if I wanted just the allylic bromination, I shouldn't have used Br2. What I should have done instead, right, was add straight up NBS. And if I add straight up NBS here, what I'm going to see is that I just get the product that I want only. And when I say only, I mean mostly. You know, there might be 1% or something like that, but way more. It's a much better product ratio, much less cleaning up you have to do, all of that sort of stuff. So same substrate, right? Same rules, right? We still have these two allylic spots. NBS follows the same rules for brominations. It always goes to the most stable place, wherever it is. So I'll look at this one too, right? Again, I have allylic versus allylic. This actually is a lot like the example I showed you before, but I have two allylic positions. One is secondary. One is secondary, one is primary. So for my product here, since I'm using NBS, I'm not going to add across that alkene. I am just going to go ahead and add my bromine in that allylic position, and that would be my product. Same thing for this one. Here's my allylic positions. And I just want to point out that this one's doubly good. Well, not only is this one secondary versus primary, but this one's amazing because it's also benzylic. So super stable place to put a radical. A great place to put a radical because it's also benzylic. So definitely my bromine would go there for your major product. And then lastly, here's a synthesis problem where it looks like I start with cyclohexene, but I have a cyclohexadiene. So I have, if I'm making notes, I have a new alkene. And for us right now, that means that I must have done an E2 somewhere, but in order to do an E2, I need some sort of good leaving group. Right, because right now we basically just know how to make alkenes from, well, E2 reactions of like alkohalides, or like a dehydration reaction of an alcohol. But since I already have an alkene on there, I probably don't want to expose it to a bunch more acid and stuff. So I'm going to go with this E2 good leaving group route. So I'm imagining that, maybe at some point in the past, maybe I had some sort of good leaving group here, like let's say bromine, for example, because then I could just add, a good strong base, T-butoxide, LDA, something like that, to do an E2 reaction, right? That could just take off a hydrogen on the beta spot to the left. But how am I going to get that bromine there? Well, I could just use NBS. NBS, and I'll just say light as my initiator. Because NBS is going to do the allylic bromination, right? NBS is going to put a bromine here. And then LDA is just going to take off the hydrogens at this spot to give me that diene. So I'm able to introduce a new alkene that is now conjugated with that first alkene. So there's going to be lots of different ways that we can use NBS. And again, it's just going to be so that you're going to want to use it whenever you see allylic brominations. Allylic brominations. If you see a bromine one away from a double bond, you want to use NBS. If you just use Br2, you're going to end up with a lot of that bromine addition to that alkene too. So do some practice. You'll see examples of these. Good luck studying.